Hello and welcome to the EMC Live webinar, Making Conducted and Radiated Emissions Measurements for EMI Pre-compliance Test. My name is Belinda Stashukevich and I'm editor of Interference Technology, the creator of EMC Live. EMC Live is an online 3-day event hosted by Interference Technology, featuring practical information and topics. This event will include roundtables, webinars, and videos on everything EMC related, and there's no cost to attend. Join us for our other webinars this week. This webinar is presented by Ken Carolus. Ken is a business development manager working for HP, Agilent, and Keysight Technologies for 30 plus years. This webinar is sponsored by our silver sponsor, Keysight Technologies. Keysight is the world's leading electronic measurement company, transforming today's measurement experience through innovations in wireless, modular, and software solutions. With its HP and Agilent legacy, Keysight delivers solutions in wireless communications, aerospace, and defense and semiconductor markets, and world-class platforms, software, and consistent measurement science. The company's 9,500 employees serve customers in more than 100 countries. This webinar is one of many this week. To check out our others, visit emclive2015.com. A recording of this webinar and downloadable PDFs will be available on our website by next week. This webinar will be interactive. You'll be able to ask questions, and we encourage you to participate. Take a look at your GoToWebinar navigation pane, the box on the corner of your screen. If at any time you have a question, we ask you to fill out the type box and hit send. To make the screen minimize and maximize, click the arrow button. To raise your hand to ask a question or to report an issue, click the hand icon. We will present the topic for 35 minutes, followed by a 10-minute question and answer session. Now Ken will begin the presentation.
Welcome everyone. This is Ken Carolus. I'm from Keysight Technologies. And today we're going to talk about pre-compliance testing on devices. There's been a lot of interest out there in pre-compliance testing that I've been hearing over this last year. So we put this together to kind of talk about it and give you some insight. So here's our agenda. We're going to have a quick overview, talk about the standards a little bit, explain some definitions, go through some measurements that we recommend that people perform for pre-compliance testing, give you some information where you can get some more demo information as far as videos and stuff, and then we're going to wrap things up. So here's EMC overview. So basically the EMI testing that everyone has to do, we kind of look at it as a smog test, because anything you put into the marketplace out there, whether it's AC powered or DC powered, has to be tested before you can sell it in the consumer market, and most all items have to be tested before you can sell it to the Department of Defense. So that's kind of why we call it a smog test. And these standards that are built to determine what performance everything will apply to is kind of slow moving because it is an international committee. You look at how things progress through our government here in the U.S., very slow to get things done. Well, now we're talking about different countries trying to get changes and adapt things. So adapting to new technologies coming out has been very slow. The equipment actually can perform measurements better than where the standards originally called out. So right now, the big interest that I'm seeing out there in the marketplace is what they call this Internet of Things. All these items you have to test. The last big move was cellular, wireless connectivity. Now we have the Internet of Things. All these wireless stuff that we have in our home and that people use. So here's the CISPRS definition. So it's actually started out as a French committee that put together this committee to do this testing. And this is because Marconi, long time ago, invented the AM radio. And when they were listening to the AM radio, they heard static noise from lightning storms. They're going, well, what is this static noise? Well, we need to investigate this to find out what this noise is in the background. So that's how this came about. And so they started looking at, besides background noise from lightning storms, they wanted to test other devices that are around. So the committee is set up to where they define what the limits are, what the test equipment requirements are as far as filtering, things like that, and the test procedures that is done to perform all the testing. So the committee itself is made up of, the main bodies of the committee is China, Japan, the European nations, and the U.S. So that's why it's very hard to get changes. We're gradually getting changes through the committee. We've just added some changes that just came out this year where they can do some fast sweep as far as a full compliance house. It's not a requirement, but the hardware that we use nowadays can, again, outperform what the hardware did many years ago when the committee was started and as they've made changes. So anyway, getting the new changes and equipment pulled into the committee and approved by the committee has been a very slow process, and it will continue to be that way. So here's some of the different product groups of the CISPRS. We'll talk about how the CISPRS standards kind of relate to the standards here in the U.S. and around the world. So as you can see here, there's things like electrical lighting. So even your lights that are in your home or in a business, they all have to be tested. Overhead power lines, broadcasting for radios and for TV. So everything that's electrical, as I mentioned earlier, whether it's battery powered or AC powered, has to be tested according to certain standards that have been defined to be sold into the different markets around the world. So here are the examples of the different nomenclatures that are used. Like here in the U.S., we use the FCC standards, but again, everything feeds back to the CISPRS standards. So we have the FCC standards, the Department of Defense standards. You'll see these little icons in the back of manuals to say that indicates that this product has met these standards, whether it's the FCC standards or if it's in European countries, you'll have EN standards that the products meet. So you'll see all these little icons that are in the back, typically the last page of the manual, explain that they met their standards for that country. Again, all these standards are based upon the CISPRS standards, but everyone wants to name them something else. So here's kind of a quick little cross-reference of some of the standards. So in the center is the list of the CISPRS numbers. Over on the left, the FCC, they'll call it FCC Part 18, where it's related to CISPRS 11. So that's the industrial, scientific, and medical equipment. So that's a big booming area right now. All the Internet of Things drops into that area, needs to be tested. You have automotive standards that are called out in CISPRS 12, but in the U.S. they actually drop in under 15 and some of these other standards. So there's subcategories under 18 and Part 15. So they break down. Over here on the right, you can see the European nations. So they have a different numbering scheme. So in here, fluorescent lights and all that. They still have to be tested according to the CISPRS standards, but there's subcategories under what the FCC calls out here, under 18 and 15 typically. So here's another breakdown, kind of talks about a little bit more the FCC standards. So equipment type, broadcast receivers, household appliances. So you can see over here on the right-hand side is FCC Part 15. So it could be Class A, Class B. So I mentioned there's sub-parts to each one of these to break down and pick up the other CISPRS measurement capabilities. Now, CISPRS standards call out conducted measurements. There's two types of measurements we're going to talk about as we go through this. There's conducted, which is over your power lines, whether it's the AC or DC power lines to drive your device or a motor, whatever. So they're tested up to 30 megahertz, as you can see here. Radiated measurements, those are RF energy that comes off the device is radiated out. Those are tested up to typically 1 gigahertz. But there are some exceptions here in the U.S. So CISPRS only tests up to 1 gigahertz. But here in the U.S., there are some conditions where we test up to 40 gigahertz. So one exception to this radiated measurement is the Department of Defense. So if you're working on two-way radios for the Department of Defense, they want those radios where the antenna connects to the top of the radio or connects to the radio. That connection point has to be tested for any RF leakage up to 40 gigahertz. Reason being is they do not want any RF energy coming out, and that could be an identifier or a footprint of the U.S. military coming into an area if they have real sensitive receivers looking for that RF energy leaking out of radios. So that's why the Department of Defense requires testing up to 40 gigahertz. Also, the FCC has a couple exceptions here where they test up higher than the 1 gig, and that's for high-speed digital clocks. So if you have clocks that are very high speed, then they have to test up to the 5th harmonic. So, for example, down here on the bottom of the screen, a computer or a radio with a 1.2 gigahertz processor has to test up to 6 gigahertz. So that's just an example. So it depends on your clock speed. Typically, this just affects the guys that are building the laptop computers that have very fast clocks that are running them. There's also another requirement under FCC Part 18 where they're testing up to the 10th harmonic, and that's if you're transmitting signals above 1 gigahertz. So if your item is actually transmitting above 1 gigahertz, then you're going to have to do some higher testing. Most of the IS&M band, the industrial, scientific, and medical band, operates in around the just below 1 gigahertz. So they're typically in the 900 megahertz band. So typically that's not an issue. But there are a couple bands that go up to 2.4, and there's one band that goes up higher than that for industrial and medical equipment. But most of the items that are in the marketplace are out there from 900 megahertz as far as a transmitter that's transmitting stuff, like for communications. So let's talk about some of the definitions and terms so you can understand a little bit better what I'm talking about here. So electromagnetic compatibility. So that's the definition of that is for devices to be able to work with other devices. So right now the RF energy out there is just very polluted in a lot of areas. So a lot of stuff going on, especially in the ISM band where all this new stuff is dropping in. So how can things work out there and be compatible with each other? So that's what that's talking about, electromagnetic compatibility. Then there's electromagnetic interference. So that's where one device will actually cause interference for other devices. That's kind of what we're focusing on here, is testing for that. And then there's electromagnetic compliance. So is the item, the device under test, whatever you're making there, is it meet the standards so it is compliant? It can operate out there and not cause interference with other items. So that's your EMC, EMI, and then compliance that we have out there. So what is EMI? So electromagnetic interference. So here's out of Wikipedia. So it calls out either electromagnetic induction. So an electromagnetic induction is conducted down power cords, conducted on a power line. Then you have electromagnetic radiation. So it's emitted from a device, radiating out. And the government actually will use EMI for jamming. But typically what we're looking for is EMI that's unintentional. So that's what we're testing for, something that EMI that typically radiates from your device that's unintentional or comes down the power lines and causes interference. So sources of EMI, you can have natural sources, electronic storms, and again, that's how this whole CISPR standard committee came about, is because of lightning storms that can hear it in AM radios, and they wanted to investigate further. They called it, it's kind of annoying to hear that in the background, and they didn't want other electronic devices to cause annoyance when you're trying to run something or listen to something. Above that, you can have cosmic noise, solar radiation, but it's very, very weak in power. But there are other natural sources out there. Now, there are man-made intentional sources. So two-way radio communications, cell phones, Internet of Things, things that are actually transmitting, broadcasting to something else. So you can call this stuff on carrier or carrier frequency. So it's an intended transmission of a frequency. It could be a beacon or a control signal to control stuff. It could be modulated, whether it's voice or data, analog or digital. So those are intentional man-made sources. And typically what you end up doing is measuring for harmonics or spurs away from the intentional carrier. So there's unintentional man-made sources. Toaster ovens, bug zappers, hair dryers, A hairdryer can cause interference with other items. So even hairdryers have to be tested. It's got an electric motor in there. Again, anything that takes electricity. So what you're looking for is leakage, RF leakage, leaking out of an enclosure. Or harmonics, if it's a intentional transmitter, you're looking at harmonics, even multiples, or spurs, the addition or subtraction of frequencies. It could be two control lines close together and they're mixing signals and causing a spur that's radiating out of a device, causing interference with other devices. There's two types of EMC measurements that we're going to focus on here. So we're focusing on the radiated emissions and conducted emissions. Now there's two other types of emission testing, so susceptibility or immunity for radiated and conducted susceptibility or immunity. Susceptibility or immunity testing is required for devices that you sell into the European market. So if your device is going global, then you need to test for that. Here in the U.S., the FCC does not require that for passing EMC requirements. They only test here for radiated emissions, so you're going to leak out, cause interference, or conducted, where you're going to come down a power cord. They figure if there's a problem here in the U.S. with a device that's sold into the consumer market, the consumers will let the company know, hey, this is not working well, and they'll stop buying the device. Over in Europe, they require testing to make sure the device is put into the marketplace, operates correctly, and will operate in a hostile environment. There are some cases where there's medical equipment that is tested for immunity here in the U.S., but that's not required by the FCC. So that's required by the medical board to put some items in the hospital. So there's still, we'll have a slide that kind of talks about the immunity testing so you can see what it requires to test that. But it is not required by the FCC. So the areas that we're talking about, again, so we're trying to concentrate on pre-compliance testing for commercial and military testing. And it can be for all types of products, all types of different classes of products, and for anything that you're selling around the world or trying to move into the marketplace around the world. So this slide here, and everyone will get a copy of these slides, and there's a lot of information in the speaker notes to the slides. So this just talks about the different measurement units. So you can see on the left here we have conducted emissions, so it's dB per microvolts. Military is dB for microamp. So radiated emissions, again for commercial, is dB microvolts per meter. And so there's different measurement techniques, but you can take and convert all these measurements back and forth. So if you have dBm, you can take and convert it to dB microvolts or dB microamps, so it allows you to convert it back and forth. And there's a lot of tools online, so if you want power conversion tools, there's a lot of them available online. So you can do some measurements and kind of get an idea of what's going on with your device by using these formulas to compare them against the CISPRS or the FCC spec limits. So there's some detectors that are used to perform these measurements. So you have your peak detector, which is very fast. When you use a peak detector with a spectrum analyzer, you can sweep through the spectrum very quickly and get results very, very fast. Quasi-peak detector is a little bit different. A quasi-peak detector actually has some capacitance to it. So it's a fast charge rate and it's a slow discharge. So it charges it up fast, fills the energy or records energy, but it dissipates very slowly. So if you have something that is that sends out a spike periodically, it may not, even though it may go above the threshold, if it doesn't stay there long enough to really charge up the capacitor to be a problem, it may not be a spike, that an RF spike you have to chase down and get rid of. But you could have very low level background noise, and again, this is called an annoyance factor, like you hear a motor, a grinder for coffee beans, and you have an AM radio in another room, and you turn on the grinder and you can hear the motor in the AM radio in the other room. That's kind of annoyance. So they kind of call it annoyance factor. It could be low level, but if it's there for a very long time, then that's annoyance, and it could fail the limits that are set up by the FCC are based upon the CISPR standard. So again, the quasi-peak detector, very fast charge, very slow discharge. So it's a different detector than you're normally used to. There's also 3 different bandwidths required to do these testings based upon the particular device you're testing and also the spec limits that are thrown in the device. And we have tools that set all this stuff up for you automatically. But you may have something that fails with the peak detector, but it may not fail with the quasi-peak detector because it wasn't there long enough to record a failure. So you don't want to be chasing ghosts or chasing problems because time is money. So that's why you should always try to use a quasi-peak detector to do your measurements. So the difference between pre-compliance and full compliance solution. So for Keysight, we have tools that use the same engine for pre-compliance and full compliance testing. But the difference in the hardware tools, as per the CISPR standard, is that the full compliance tool has pre-selectors or a whole bank of filters in the front end. So that filters out all your ambient noise that's out there. So it basically helps filter that out. Also helps increase the sensitivity for very, very low level signals. But the main idea is to filter out all the ambient noise. So the pre-selectors, or these bandpass filters, as the instrument is sweeping across the spans there, across the frequency spans, these filters track along. And so you're just measuring the bandwidth and the signals of interest as these filters are kicking in. So you're not looking at all the other noise that's not being added into the measurement. Pre-compliance, you don't have that, but you still have the same measurement tool. So there are ways to work around the ambient noise that you have in the background. So that's the biggest problem that you have being a pre-compliance tester out there. You're working on a bench, you want to test your device, you don't have the funds to be able to buy a full compliance solution. A full compliance solution is typically 3 times the cost of a pre-compliance solution. So, and we'll talk about the measurements. So here's some of the tools that they'll use for doing the measurements. This antenna here, or a log periodic antenna, is very important to use a proper antenna when you're trying to do your pre-compliance testing. These are the same tools they'll use in a full compliance house. For pre-compliance testing, we always recommend everyone get some little close field probes to actually troubleshoot. So this is, you'll hold in, I'll have a picture kind of shows where you take and hold these probes in very close when you're searching for the problem. Down here in the center of the bottom, there's a LISTEN, line impedance stabilization network. This is where you plug your device. If it's a AC powered device, you plug it into this, and then this plugs into your house mains. So this filters out any noise coming in from the house mains. So, and then you connect the spectrum analyzer up to a port here on the front of the device, and then any noise on that coming down that power cord will be measured by the spectrum analyzer. So one thing I always try to remind everyone, when you take your device in to be tested, or when you're doing your design of your device, if you're using house power, be sure to use as short of power cord as possible, because a long power cord is an antenna, and that's going to cause you problems out there. I've talked to people that have had failures, and what they did, these were conductive failures, they had to shorten up their plug-in, the AC plug-in cord, to make it shorter so it wouldn't pick up noise and cause them to have failures that way. So always use as short a power cord as possible. And these LISTEN devices, you can find them. Many manufacturers will take and make them. Keysight does make close field probe sets, and there's also many other manufacturers out there that will also make the close field probe sets. This slide here just shows some more antennas that are used in a full compliance house when they're doing measurements on devices. Sometimes they actually have to come out to a site if something's too large to take into them to be tested in their facility. So let's talk about some of these measurements. So the main thing we're trying to stress here is that if you can do the design changes in the early phases because you have leakage, RF problems. It costs a lot less than if you wait till the product's all the way to the end. You're getting ready to go to production. You take it into a full compliance house to have it certified, and everything has to be certified. You cannot certify yourself. You have to take it in to a compliance house, have it certified. It costs a lot more to do the changes here, to do a PC board turn or to reroute cabling, things like that at this end than if you catch it earlier. So that's the value of doing pre-compliance testing as you're developing the product through the design cycles. And I have never talked to anybody, and I've talked to a lot of customers out there last year and a half about pre-compliance testing, and nobody has ever passed going straight to a compliance house unless they've done pre-compliance testing. So in the pre-compliance testing houses typically charge $2,500 to $5,000 to test your device. So you want to try to ensure that when you go there, you're going to pass. If you do not pass, they're going to give you your list of frequencies that you fell, and then they're going to say, thank you. Do you want to schedule to come back in? You can say yes. They go, okay, well, we got an opening in 2 months. So that's going to delay your project by 2 months. So you got to keep that in mind, too. You got to keep going back to try to get through and get certified. So you want to minimize any RF leakage that you have. Try to increase the product getting through the first time. So again, just to stress here on this slide that anything you make out there that's sold in the consumer market that has power to it has to be tested. That has voltage to it. Has to be tested and certified. So the measurements we're making, radiated emissions, you have to use a spectrum analyzer. Conducted emissions, you use a spectrum analyzer and a listen to do the measurements. You can put a limiter on there so you don't have a spike come in when you turn your device on, pulling power. So that's why the limiter's on there. For immunity testing, radiated immunity or conducted immunity, what you're going to need is a signal generator. And the power meter takes and maintains the absolute power transmitted out of the signal generator so they can monitor itself. And so you're bombarding your device with RF energy to see that it can still operate according to the standards that are set up. And all these standards are called out, and you can take and look them up. And then conductive immunity, over there you're going to use an oscilloscope to take and look at the readings coming off the transducer. So again, you're going to bombard the lines going into the equipment, how much energy, RF energy can it withstand before it does not operate correctly. So for the European market, you need to do this type of testing, and also for the medical market here in the U.S., but it's not required by the FCC. So setup steps to do the measurements, so the conducted emissions, you're going to connect up to your device through a listen. Your device is going to be off. Then you're going to sweep using the peak detector. The reason you're doing that is you're trying to identify the ambient signals that are out there. And then with the ambient signals, you can record the data. Then you're going to turn your device on, sweep again. You can identify what's the ambient noise, the background noise, versus what comes from your device. Then you can use a quasi-peak detector to measure your device. If there's no failures, your job's done, which doesn't usually happen. Then you have to go in and start doing some troubleshooting. And we'll have a slide that kind of talks about that. So this is just kind of going through the same setup. Hook up to a listen, so you're going to do a sweep. Then you're going to start to scan. DUT's on, so you can check for failures, and then you're going to take and go in and the individual points that fail that are not ambient noise, you're going to remeasure using a quasi-peak detector. Again, the quasi-peak detector is slow because it's a capacitive type detectors. So for radiated emissions, this is how they set it up in a full compliance house. So they have your equipment under test. So they'll test you to 3 or 10 meters from your device. They have to change the azimuth, so the vertical and horizontal. They'll do measurements at both of those points. They'll also do measurements at 1 meter off the ground and 4 meters off the ground. So for pre-compliance testing, what we recommend is that you set up 3 meters from the device, 1 meter off the ground. You can take and rotate your antenna but you need to be sure to also spin your device. So they will check at many points as they turn this device around. You can use a table, or you can just take and rotate your device around. Some items that are very large, they'll actually put a bunch of antennas around a device like an automobile. So there's a lot of testing with automobiles nowadays because all the RF products in there. So they'll take and test those with multiple antennas around them and connect it up to a test set. So again, you will do your sweeps. Then you'll take and with your device off, you'll turn your device on, you'll sweep again, you'll identify the ambience. And then we actually have tools that you can identify what the ambience are and tell it to remove it from the list. And then you're going to go in and remeasure again with the quasi-peak detector. Now, one thing down here, you can see that the noise floor is flat on these three screens on the bottom. Up here on the right, it actually has some curvature to it. That's because up here on the right, the correction factors have been entered for your antenna. So always be sure to enter your correction factors. Every antenna that you purchase will have correction factors. If you don't enter those, you may have failures, indicated failures down here that really aren't failures, or you may have areas that are close, but they pass, where if you had the correction factors for the antenna, they would actually fail. Because the correction factors, all antennas have gains and losses across the frequency span they operate across. So you should be able to look at a noise floor and see that there's a curvature to it or change to it. It should not just be straight across like you see in the bottom screens. So right off the bat, you can look at your setup to know if it's correct. Different environments you can test in. I've seen testing on benches. There's TIM cells out there, whereas a shielded box, you can put a device in to test. You can have an open air test site where you can do testing outdoors. Again, you need to take and record your ambience and then eliminate them from the testing with a quasi-peak detector. And a lot of companies are starting to build small RFI chambers. I've actually been to a company that built a chamber that was made out of fencing. So you're trying to build a Faraday cage around your device to eliminate the background noise, RF signal, to try to just concentrate on the energy, RF energy coming out of your device while you're testing. Talks about problem solving and troubleshooting. Nice thing about new spectrum analyzers is you can have multiple traces. Old spectrum analyzers, you did not have that capability. So you can actually do set the frequency to the failed frequency you're trying to troubleshoot, do a sweep, capture that, then go and make your changes, whether it's moving a trace, rerouting cabling, maybe you have to put in some more shielding. Then you can come back and do live measurements and then recall that trace that you saved to see if you're gaining or losing on your changes that you've made. This kind of walks through those steps. And again, you'll all get copies, have access to copies of these slides. And then, so here's using a close field probe to take and check for failures, go in and measure where the problem's coming from. We had a problem years ago with our signal generators. It was actually the torque setting of the Torx driver to tighten the screws around these clamshells that we had these RF boards in. And because we did not have the torque settings at one station set correctly, the screws weren't tight all the way down. We had elastomer between these clamshells. So the RF signal was leaking out. We were chasing that one for some time before we finally determined it was the settings on a screwdriver to drive in the torque screws. So you need to have the close field probes so you can go in and see where it's leaking at to help you determine what's causing the leakage itself. Again, always have a good set of close field probes to use that for troubleshooting once you've identified you have leakage. You can make your own close field probes, but that's in a pinch. If you do make some because you have multiple people doing troubleshooting, still within your facility have one good set, whether it's from us or somebody else. Always have a good set on hand because they're calibrated for the frequency range you're trying to measure across. These, if you make your own, you don't know what frequency range they're calibrated for. But this kind of shows how they're made. So the next three slides, I'm not going to spend a lot of time on them. That just kind of is available. You guys can go back, look at it. So these are design practices. So this talks about device selection. So if you're selecting devices, this actually came from our lab engineers over the years as kind of a check sheet that they keep up to date, like avoid IC sockets whenever possible, use surface mount parts whenever possible, things like that. Keep cables as short as possible. Next one talks about PC board layout, and again you can see there's a lot of good information in there. Talks about filtering, how filters should be placed. Do not route clock traces next to the edges of the PC boards. So a lot of good input on that. And mechanical design, avoid dissimilar metals, avoid requiring large holes in PC boards, avoid long lines to motors, and always twist your motors, your power lines to your motors. If you don't twist those wires together, that drives your motors. If you have something that takes a motor to operate, that's going to radiate RF energy and cause you failures. So always keep those lines twisted. So for demo information out on YouTube, we have a lot of good information out there for the customers to just kind of see how measurements are performed. So you can go out there to the Keysight site and just do a search on EMI or do a search on our products, like this one here is around the N9000A, and there'll be a YouTube link, and you can look at pre-compliance testing. It kind of goes through the measurements. And there's also some information out there on using the probes, how you go in, and they'll actually troubleshoot a computer, kind of show you how you go in and use the probes and get narrowed down to different probes, and you can find exactly where the leakage is coming from out of a computer that was leaking. So some good examples, some good stuff to view. So be sure to always go out and look at the YouTube videos. So we'll just kind of do a wrap up here. So again, the EMI can be a bottleneck from your process being completed. You're trying to get stuff to market. Time to market is critical. If you spend time looping around with a compliance house, you're losing time. So it's typically a worthwhile investment to do some pre-compliance testing. And we do have tools that have the same measurement engine as a full compliance, so it kind of gives you a good understanding of how the full compliance house is doing. It's very inexpensive software license key to turn it on if you currently have one of our test sets. And everyone has to do it out there. Again, do your testing through the full design phase of the item that you're trying to bring to market, because you want to get it to market as soon as possible. Identify those problems up front before you get all the way and have to start doing some redesigns later in the process. It's a lot more expensive to do that. So I think we're open now for questions.
Great, thank you so much, Ken. We'd like to have a call for final questions. Please enter any last questions you may have in the navigation pane. We have received quite a few questions on where to get additional information on this topic. There's a vast amount of content found on our websites, emclive2015.com and interferencetechnology.com. You can also email us with specific needs and we can direct you accordingly. Ken, here's a question for you. Is the quasi-peak detector hardware or software?
So the quasi-peak detector is actually hardware in a spectrum analyzer, so it's not software. It's not a calculated value. Again, it's a detector like a peak detector, but it's also a capacitor that's built into it, so that's what makes it unique.
Okay. Can you use a peak detector instead of a quasi-peak detector?
You can, but as I mentioned earlier, the quasi-peak detector can actually identify true failures versus a peak detector. You may have a failure with a peak detector, but the quasi-peak detector measurement would say, okay, this isn't there long enough to cause a problem. The annoyance factor is low. So you could end up spending time troubleshooting signals that you shouldn't have to spend time on if you had a quasi-peak detector and used it properly.
Okay, here's another question. Do all spectrum analyzers come with a quasi-peak detector?
No, typically a quasi-peak detector is optional within a product. And some of the older spectrum analyzers out there, whether it's the old HP ones or the Agilent Keysight spectrum analyzers, there are some older ones that do not have a quasi-peak detector available. So you need to check on your specific spectrum analyzer to see if it is available. Now our new series, our X series analyzer, it is available in all of our X series analyzer, and in those it just takes a license key to turn it on because it's already built in with our bank of detectors that we put in the product.
Great. Typically, what is the cost difference between a pre-compliance solution versus a full compliance test solution?
So briefly, I mentioned there that it's about a three to one factor, 3 times the cost. So for example, a pre-compliance tester like the one you're looking at here for pre-compliance will run, if you're starting from scratch, buying the hardware and everything, it's about $18,000. So that's for a 3 gigahertz solution. For a full compliance tester, a 3 gigahertz solution will typically run $34,000. And just like, for example, a 26 gigahertz pre-compliance tester will be about $61,000. For a full compliance, about $115,000. So big difference. That's why going into a pre-compliance house costs significantly to get your device tested. But your costs for pre-compliance would be a lot less than trying to buy a full compliance solution, unless you really felt you had to have the filters.
Okay, we have another question about products. Does Keysight offer both pre-compliance and full compliance solutions?
Yes, we do. So we have our X series family that we've had out for several years, and so we have from 3 gigahertz clear up to 44 gigahertz solution for both pre-compliance and full compliance. So whatever your need, we have you covered there. And pre-compliance, the measurement app, if you currently have one of our X series analyzer, it's a little less than, it's right around $5,000 to turn on the measurement capabilities to turn on this solution here.
We have another question from our audience. Is testing
Any other question?
Yes. Is testing required for Part 15 Class A devices?
Yes. So again, anything that has any kind of AC or DC power has to be tested. Just think of it as a smog test. Everything's tested out there.
Great. We have a lot of questions coming in. Let me take a look. Is the use of preamplifiers required when doing EMI measurements?
It's not required, but preamplifiers are available, so that'll again increase your sensitivity and by amplifying the signals from the noise floor. So your signal to noise ratio will increase using preamplifiers, so you can pick out some of the weak signals a little bit easier from the noise. And on here on the display here, you can kind of barely see a line where the threshold is, so that's for Part 15 sweep, so you can see where the noise floor is versus where you have some failures in the red indicated thresholds there.
Great. Are narrow band limit average detector mandatory by CISPR?
Yes, it is. And we have that in our full compliance solution, and it's also available in our pre-compliance solution.
One more. How important is it to calibrate antennas used for radiated emission testing?
It's important to have the cow factors in there. So you're not calibrating the antennas, you're purchasing antennas, and there's several very good suppliers here in the U.S. that make antennas. TDK, ETS Lindgren, they make very good antennas. They all have cow factors built around their antennas, and you just need to be sure to put that in when you're doing your actual measurements. Because again, you could have a failure where if you don't have the cow factors in there, you may think it passes, you take it into a full compliance house and you have a failure.
Great.
Critical to put those in. Yep.
Thank you. We have received so many great questions we will try to address in the future. Ken, thank you again for your time and expertise. Please join us for EMC Live 2016, which takes place next April. Webinar attendees, if you have any more questions we didn't answer here, please send us an email at info@interferencetechnology.com. A recording of this webinar will be available on our website, emclive2015.com. We will also send a link to all participants shortly. Thank you for attending.